Let us now look into one of the most important topics under the machine learning course. We are now talking about overfitting, regularization, and hyperparameter tuning. Now, these names might be new to you, but then I would ensure that by the end of this section, you will be comfortable in understanding these concepts, as these are extremely critical concepts for the course. Now, let's start with a very brief introduction to this topic. We have four different terms that we need to get acquainted with: overfitting, regularization, hyperparameters, and hyperparameter tuning or optimization. Now, while we were understanding the evaluation metrics for a classification use case, we talked about overfitting and underfitting. Those were two new terms which came across in the previous section. Let's understand what would we actually mean when we say overfitting and underfitting. Now, if you try to split these terms, overfitting, it is over and fitting. Fitting is generally the process, let's say you're talking about linear regression. Fitting would be the process of fitting a line. So you're finding the best line and the associated parameters for that particular data set. In the case of logistic regression or a classification use case, you're saying when you're in the process of fitting, can be defined as finding the best parameters that define the relationship between the y and all of the independent variables. Now, in some cases, in fact, in most cases, your data won't really be clean. When I'm saying clean, it would actually have a lot of noise. The noise can, in terms, can be defined in terms of some random patterns which really don't make sense, some outliers, and something which really you can't help. So let's say if it is an outlier, that's something which you can really treat and process. So that can be taken care of. But then beyond that, beyond business domain, there are a couple of patterns which really don't explain anything, and you really can't do a lot about the data. Now, in such cases, it kind of creates a complicated relationship. So what happens is, because of these noise in the data set, the model tries to learn a complex relationship, and in that process becomes extremely overfit. Now, when I'm saying extremely overfit, it kind of memorizes the model. Now, how do you identify that it has overfit? So what will happen is, let's say you have 100 samples for training, and out of these 100 samples, you have created a test and a train sample. So you have divided them into, let's say, 70 and 30, using 70 for training and 30 for testing. This 30 for testing would be the unseen data. Now, in cases of overfitting, what happens is, when the model is learning from these 70 training samples, it creates an unnecessarily complex relationship. So in that process, it performs extremely well when you're trying to predict the seen data, that is the 70 data, the 70 records of training, which are just used for the purpose of fitting. But then when you bring in an external unseen data, it kind of performs miserably. So if you see the performance between the trained dataset and the test dataset, you'll see significantly large differences. That's because the model has failed to generalize. So when you're talking about overfitting in simple terms can be defined as the phenomenon in machine learning when the model gets too complex and fails to generalize. So technically, there would be noise in the dataset, and instead of ignoring the noise, it actually treats that as a part of the model and then tries to create a complicated relationship. And in that process, it actually goes and overfits. So it performs exceptionally well in terms of predicting on the seen data set. But when you put in some unseen data set, it performs miserably. Uh, Another intuitive way to understand overfitting would be: consider you're teaching a child to predict the pattern. So let's say there's a child of, let's say, a 5-year-old kid, and I was trying to predict what will his mother cook for lunch today, or what will his mom cook for breakfast today. And let's say his mom would either cook pancakes or something else, and this kid is specifically interested in pancakes. So he's predicting whether mom will cook pancakes or not. That's like a classification use case which you can simplify as a binary outcome. Now, let's say for simplicity, every day the boy has been measuring some data. So every day 8 a.m. He looks into the kitchen and asks mom what is there for breakfast. Okay, fine. Let's say on Monday, Wednesday, and Friday, he found mom making pancakes. He kind of creates a rule. Okay, if it's a Monday, Wednesday, or Friday, the outcome is definitely going to be pancakes. If it is not any of these days, it would be something else. It would not be a pancake. So this is the simplified rule which he has created. Let's say over a period of time, one day, randomly mom made pancakes on a Tuesday. Now all of a sudden, this guy got confused. He said that according to my previous rule, it said that Monday, Wednesday, and Friday we have pancakes. But then all of a sudden, Tuesday, mom has made pancakes. So now Tuesday actually might be an error. It would have been something random which has no explanation, and the best would have been to actually ignore that and stick to his previous rule, which is Monday, Wednesday, and Friday. It is the mom would serve pancakes. Rest of the day something else. But instead of that, he actually goes ahead and creates a complicated rule. Now, this complicated rule can be termed something like, let's say, okay, Monday, Wednesday, and Friday, pancakes. But if it's the first day of the month and it is a Tuesday, then it will be pancakes. Now, just to fit this random data point into his existing protocol, he kind of creates an unnecessarily complicated rule. And let's say in due course of time, he just adds in more and more complicated rules. As and when came up, he encountered with a couple of spurious use cases. Let's say one certain day or one fine day, his mom did not cook pancakes on a Wednesday. So his traditional rule is okay, fine. If it's a Monday, Wednesday, or Friday, it would be a pancake. Or if it is the first day of the month and it is a Tuesday, it is pancake. But then all of a sudden, you see, okay, fine, one new data point, which can be treated as an error. But then you see, okay, fine, Wednesday, and it is not pancakes. So then probably he would just create another complicated rule. That would be Monday, Wednesday, and Friday, and the first day of the month if it's a Tuesday, and if it's a Tuesday and if the day is an odd day. So some random rules, you kind of create complicated rules, and in the process, he fail to generalize. That's the process of overfitting. So what's regularization? Now, a technique used to reduce overfitting by introducing a penalty that punishes the algorithm while letting the parameters get too large or complicated. Now, just recollect the same example I was talking about. Now, you have a scenario where you have created unnecessarily complicated rules, so your model is overfitting. Now, whenever you kind of misclassify or you incorrectly predict something, what if there was a mechanism to actually give a signal or a penalty so that the algorithm understands that this is incorrect and probably it's best to ignore. So if you go back to the child and pancake story, let's say he created the rule Monday, Wednesday, and Friday, mom would cook pancakes, rest all of the days something else. But then one random day, mom cooked pancakes on a Sunday. So instead of creating a new complicated rule, so in the process of creating a new complicated rule can be analogous to increasing the impact of a parameter. So let's say you have the beta coefficients of each parameters, and probably unfortunately one of them would actually scale up to accommodate these new random changes. And then the outcome actually kind of gets impacted for when it fails to generalize. Now, in such scenarios, regularization can be used where a technique is put in place where the moment uh, you're trying to overfit the model, where you're trying to create a complicated rule, it tries to penalize that particular parameter. And that way, like through a signal process, the machine learning algorithm understands that like okay, this needs to be generalized. So that's a technique where you can reduce overfitting and you can make better models that are more generalized. Now that's regularization. Now, how do you do it? One of the like there are several methods to implement regularization. One of them is actually to use hyperparameters. Now, hyperparameters basically are metaparameters which are associated with the learning algorithm. Now, please don't get confused with parameters of the model and hyperparameters of the model. These are completely different. Hyperparameters are defined as the metaparameter. So for example, let's say for logistic regression, the beta coefficients would be the parameters of the model. But then hyperparameter would be a parameter that helps the learning process improve in such a way that it generalizes. So something, let's say like so in logistic regression, you have under scikit-learn, you have a parameter called C, which controls the inverse of complexity. Now, that C could be a value which kind of uh, gives a penalty to the parameters when they try to scale up to accommodate a complicated rule. Now, we can introduce regularization into an algorithm with the help of hyperparameters. Another simple example of hyperparameter would be for, let's say, decision trees. So for decision trees, if you define a number, let's say the maximum depth of the tree. So if you say the maximum depth of the tree to be, let's say, 5, and within each tree, let's say when you talk about the leaf nodes, now the number of leaf nodes, there would be criteria for leaf nodes. That is, if you're trying to split a node, it should have minimum n number of observations. If you tune these observations, let's say if you increase the number, if you reduce the number, it kind of automatically incorporates generalization. So these are hyperparameters that help the learning model implement regularization. Now, hyperparameter, as you know, can take different values, and finding the best value that will give us the best result, that's called as hyperparameter optimization. So out of a list of couple of values, you're choosing the best value, which can be treated as the best hyperparameter value for that use case. So that's a brief introduction. We looked into we took a shot at understanding the process of overfitting. We understood what is regularization and how we can implement regularization using hyperparameter and improving the model using hyperparameter tuning or optimization. Let's move on to the next topic.